Hello everyone, welcome to this presentation. So today we are going to walk through how we designed with COMSOL multiphysics of BAYZ Audioo's new tweeter. So that's what we are going to discuss and walk through. And welcome everyone here. So my name is Arpad Forberger. I'm an application engineer at GAMAX Laboratory Solutions. So we are doing R&D, research and services in Hungary and the surrounding countries for more than 20 years now. And today we are going to look through what is COMSOL multiphysics, what different physics, what's the phenomena behind what we need to include, and then the model description. How does it look like? Which parts do we need? What assumptions can we make? And then we will walk through about the model, how to create an application from that, and what the results are, and summarize the presentation here. So just a few slides about COMSOL multiphysics. That's what we used for designing the tweeter, the speaker itself, since it includes and it needs to include several different physics. So COMSOL is based on solving equations, PDEs, ODEs. It's not specialized on any like structure mechanics code, so it's a general tool for solving equations like in electromagnetics or fluid flow or acoustics, and we can combine them together freely. So that's where the name stands for. So we can create coupled physics problems like a speaker design here, and we can also couple into optimization. So there is no restriction on that, so we can use it for finding an optimal shape or design for the magnets and so on. So it can be used for any objective function if you wish to optimize your design. And also you can, and we will see how you can create an application from the model. So any model can be turned into an application, so we can compile to an executable, and the full complex finite element model and its graphical user interface can be reduced to a custom-made interface. So we can create that one easily. Okay, so that's the core COMSOL package. Just another slide here. So different physics and what we want to include and what it has to be included in the model is used for the AC/DC module from the electromagnetics branch, and we are using the structure mechanics module since we have solid and flexible domains moving around. We have the shell interface. There are thin structures that can be modeled as shells, and we also have the acoustics itself, so we can calculate the radiation pattern and certain properties that are relevant for us, in this, like the sensitivity and for the impedance curve. And we use the COMSOL compiler, so that creates our application, so we can create an app from that. So these are the few of the acoustics interfaces that are available. So there are predefined interfaces for different applications, for pipe acoustics or for small devices like mobile phones and microphones, where you need to take into account the viscous dissipation on those layers. So that's also included. Those nonlinear effects are included. And it can go up to other dimensions, to geometrically large problems like auditoriums or opera houses. So that's another interface where you can calculate the eigenmodes of those rooms also. So from microphones to opera houses, there's a wide range in geometries. So everything can be solved there in one piece. And if we go down to a level where we cannot neglect the viscous dissipation, that's also possible to do that. So these thermoviscous acoustics that can be incorporated and included, like you can see here a little snapshot. So if you have small perforate meshes, they are about in the range of millimeters, then we can include that one also. And it's just a few snapshots what's all included. It's for speakers, for the cabinet design, for microphones, and there are lumped parameters that can be incorporated. So if you want a lump representation of the microphone or the speaker or both, that's also possible and included. And if something is not predefined, then we can add our own equations. So it's, as I started with, so it's based on solving equations, PDEs. If you have your own equation for any boundary condition or material property, anything that can be included here. And it can be also used for like the optimization for various purposes. On the left, you can see the spider optimization to find the linear formulation for the excursion of the coil. It can be used for topology optimization for a magnet, for example. And you can include different constraints, milling constraints that it can be, and it should be manufacturable. So that's also possible to do that. And for parameter estimation, so sometimes not all of the material properties are available. So we need to use the data from the measurement data, and we can find the missing properties with the optimization parameter estimation problems. So we can match the measurements data with these. Okay, so let's jump into the model itself. So this is how the speaker looks like. Not all sets are there. So we have the membranes. As you can see here, it's not the traditional axial symmetric geometry. So we have an extrusion in one dimension. In this dimension, then we have the PCB that holds the coils. In this model, it's a two-layer, double-sided PCB with the coils on it. And then we have the magnets there and an iron piece there. And also we have, which is not here in the figure, so we have the suspension. And for the first assumption, we assume that we can use a symmetry plane here in the middle and take a cross-sectional view of that and use that for calculation. So, and after that we can check the validate whether this still holds, this still valid for that assumption. And we can reduce. So here in the both sides, so we have the suspension, so we can reduce that into a boundary condition. So we don't need to explicitly model that one. So we can assume that from our structure mechanics knowledge from the university studies, we can create and we can use this suspension and we can turn this into a mass spring system. And from the deflection, so we can, it's quite a simple load, so we can calculate the equivalent stiffness of the model. So we don't need to explicitly model, but we can use as a boundary condition. And then since the where is it? The mass of this one. Okay, so the mass, I can go there. Where is my, oh, it's missing, okay. So the mass, okay, so the mass of the suspension is comparable to the other parts masses, so we cannot, if you want to create an accurate model, we shouldn't neglect the mass of the suspension. And so we assume that the equivalent system has the same kinetic energy as the original one, and with simple calculations we can assume that if we take 1/3 of the suspension's mass and we add to the full system, then the two systems will be equivalent in the sense of kinetic energy. So we can assume that this assumption is valid there. Okay, so that's what we see here is the current and the full graphical user interface where we can see all of the objects. So we have all the relevant physics set up here. So we have the magnetic fields that solves for the magnetic field itself, the flux density with the coils, and we have the pressure acoustics interface, and we have the solid mechanics interface. The solid mechanics that holds for every part that are solid. So here, these are the 4 magnets with these greens, and these are the iron pieces. We have the membrane here, and here in the simulation, so these are considered as infinite baffles. So that's how it calculates the far field pressure field, and what we calculate as the magnetic field, then this, what's happening here? Then this Lorentz force coupling, so that handles the connection, the strong coupling between the moving coil and the magnetic field. So it calculates the force that is acting on the coil, it starts moving, and it creates, this moving coil creates a magnetic field around itself, so it weakens the field that it's created, and this Lorentz force coupling, it handles this two-way coupling automatically. And that creates a movement of the solid parts, and with an acoustic structure boundary condition, so the two fields, the motion is coupled to the acoustic field, so you can calculate the radiation pattern, the sensitivity, and from the AC/DC calculations you can calculate all the relevant curves like coil resistance or the sensitivity and an electric impedance curves there. And for the solid mechanics, so we have some material properties. They are from tabulated data. Some properties are missing, so we need to guesstimate those to have some first iteration about those. And we also have the damping and the losses for some of the materials in the solid mechanics interface. And technically that's from the physics side. We have different study notes for different calculations. So the study starts with calculating the banded shape for the membrane, and then so we have the solution for that one. Then it creates the geometry, solves the problem, sets up the static magnetic field, so that will be used for the linearization point for the frequency domain study. And then we get all the relevant figures here, so that's handled automatically there. And there are other components and other study notes for calculating the distortion of the model and some other coil features. And we can also calculate here, the model also calculates the natural modes, the eigenfrequencies of the system, so we can have an understanding what are the eigenfrequencies here. So this is the full model with all with the full graphical user interface, and we can turn this into an application. And for the modeling workflow, so we start with the suspension. So we create an equivalent model of that to have a 2D representation of the full 3D model. Then we can set up the 2D model by first moving the right points of the membrane to the desired position. Then we can calculate the deformed shape of the model, and since it's a large deformation, so we need to take into account that it's geometrically nonlinear problem, and also since it's a membrane, so we need to avoid that it should have just a unique solution, otherwise it turns into a buckling problem. So numerically it's not possible, not that easy to solve that one. So we need to make sure, we need to ensure that it has just it has a unique solution there. Then we build up the geometry, run the study, and we can plot the results there. So for that, so there are several steps: creating the geometry, solving the bending problem, setting up the geometry, setting up the physics. So we can create methods. So here, this is the traditional, that's the full graphical user interface, and we can create custom user interfaces, so we can hide the model, but the functionality will be there, and we can create a custom user interface for that, to do that. And for that, we can also create methods, so we can group together different steps together, and we can turn so here what we have seen here, so this is the model builder where we build the model, and we can turn this into the application builder where we create an application. And here you can see, so we have different items for the top ribbon menu, so we can customize them, what we want to do there, and we can add our forms. These can be forms for just information, to plot the shape and the geometry, how does it look like. And then we can also create the main graphics windows there. So we can have several graphics windows, we can freely organize them together. And here also we have the methods. Here you can see a snapshot of that. So if you have, let's say, a drop-down menu when you can select different materials, it can run a series of commands. So you need to assign those materials to several places. And you can do this by applying these codes there. So you can access everything from the model with these notations there. And all of the parameters are available, so everything can be used here as an input. So we have almost, everything is parameterized, material properties, geometrical properties, and they can be used here freely. Okay, so how does it look like? So that's the model itself, and then we can use this application builder interface. So that's the model builder, and we can switch to to the application builder interface, and then we have the forms here. Okay. And we have the inputs. So we have much fewer parameters than the original versions, but all the necessary parameters can be here and can be adjusted. And then when you select some of the buttons, you can see a series of commands that will be executed. And here, the first one is for creating the deformed shape. So it will calculate the deformed shape for the membrane. Then you can go on and you can calculate and update the geometry. But if you don't know something, you just simply record the code. So you just click a button and everything what's happening on the user interface will be recorded. So if the user wants a button that will disable or enable certain features, you can record that feature with just a click of a button, and you go back to the application builder, and then the code will appear there. So you can use any of the features from the full model, and you can transfer them to the graphical user interface. And you can also test the application there. So that's the basic idea behind, and that's the simplified version. So that's the application builder, so a custom graphical user interface can be used. So here at the top, all the buttons are available. That was in the requirements to calculate the geometry, build the geometry, calculate the frequency response. There is some sort of optimization inside to find an optimal shape for that, to get a flat response. And you can calculate the distortion, the radiation pattern, and then there is a results section, so certain buttons for certain plots to plot the sensitivity, directivity, the radiation pattern in 3D, and here we have many of those graphical figures that can be used there. Okay, and how do we create this application? So I recorded a sample here. So that's one of the built-in examples. So you can just go to the application builder, and you can start from scratch. So there are built-in templates where you can do this, and by simple drag and drop different forms and different parameters, you can create that one. So you can start with the templates if you wish, but you can fully customize them later. Some of those are optimized for smartphones, some of them for computers. You can put a switch on that, whether it will run on a computer or a tablet. So the graphical user face will adapt for that, and you can use that one. And then all of the parameters are available, and just simply select what should be on the user interface. And then you will get also a preview here, so how the user interface will look like. So whatever you put in the parameter list, those will be available here, and you can just select those. You can also use the derived values as an output values, so not inputs. And from the geometrical node to the results node, anything can be used as an output there. So you can use a graphics window, and here you can plot, let's say, the sound pressure level. And then you can add the study nodes there. So you want to compute a shape optimization model, and this is how the model will look like. And then you can rearrange the buttons, and that's it. So that's technically how you create an application. And you can always check what will happen when some of the buttons will be clicked there. And you can also test here. And you can always check that the plot will be handled to the first graphical window. So technically, that's it. You can select the forms, and then you can just drag and drop the methods there. Yeah, so I just added another one here, so we can rename it, and then we can select what should happen when you click the button there. Let's say we want to plot the pressure, the sound pressure level, and you just select from the results node that whoever clicks this button, then the sound pressure level should be plotted. Yeah, and we need another plot, and we need to select into which graphics window should we plot those. And that's it. We have only one here, but you can have several of these windows, so you need to decide where this should be put. And that's it, technically, how you create this application. Okay, so now this is the actual application that is built on the full model. So here you can see the items that were in the method editor. So these are, the first one is to create the geometry, to set up the geometry. So starting with the deformed shape, so calculating the deformed shape, then updating the geometry. There are some informative panels that plots out what are the dimensions. Then here in the main section, here we have some other panels for input parameters, for study settings, for the coil parameters, results, and so on. So these are the available values. So we can switch to a closed back version or rigid ends. By default, it assumes that it's glued, so the membranes are glued to the baffles, but you can switch to the rigid representation. And also, there are some other options for the coils. You can change the coil, the default copper representation to aluminum coils, and you can switch the PCB to different versions, and of course the membrane materials can be changed. And for a certain setup, this will be the sensitivity curve, and here you can find all the results plot. They can be drag and drop, they can be detached to a secondary window if you like. And then in this second plot we have the displacement magnitude here in microns for a certain frequency, and you can play the animation and you can export and you can find another one. So there are many options there what you can plot there, and it's much simpler than the original, than the model's user interface. Okay. Okay, so here, that's the first part when you open up the model. Then, oh, sorry. I just can't find my... So first we need to create some initial geometry, then we need to calculate the deformed shape. That's the first case, and since we don't have the deformed shape and we don't have geometry there, so the icons will automatically... So here the icons will automatically change the deformed shape and the update geometry to an icon with an exclamation mark. And then as soon as we have the shape, then the deformed shape will change, and then we can update the geometry to calculate that one. So that's the first session here. So we can, it's here. Let's speed this up. Okay, so during the calculation, so it will plot the shape of the membrane, and we can see the equivalent stress in the membrane. And then when it's finished, so we can find the solution. So it's in the right position. Then we can go to the geometry, and then we can update the geometry itself. So it will run a series of commands. They are put in the methods, and it will create the geometry for us. What's happening there? Okay, so now this is the geometry. So this is the 2D representation, and then you can change it to a closed back design. So you can include porous material behind the membrane if you wish. So you can create calculations based on that one. And you can change the material, you can change the coils, and so there are some options that are changeable there. And then when you set up the study with the start frequency and the number of steps in each decade, then you can compute the frequency response and you will get the results there. These are the default ones that can be plotted there. And I selected some of the plots. Here we already had some. So here we had two. Here this is the displacement magnitude for a certain frequency. Here is the sensitivity for a certain geometrical setup. And then we can also plot let's say, the displacements at different frequencies. So there is one selected for 500 Hertz, and we can also calculate the eigenfrequencies, the eigenmodes. So that's also possible. So that's one mode for at 800 or about 800 Hertz. So that's also possible to plot there, and we can also plot the results from the magnetic calculations. So we can plot the the flux density inside the motor. Here you can see the upper part is hidden because we don't want to use that one for any sort of calculation. It's not important for us. And there is another one. So there is the radiation pattern plot. So here you can find a sketch of the membrane and the PCB. And for a certain frequency, you can see how it will radiate in different directions. So that's also possible to calculate. And of course, what we really want to see is the directivity. So here are some certain frequencies. They are pretty close to each other. So it's 0 degrees, it's front of the speaker, and it's plus minus 90 degrees. So it's 180 degrees in front of the speaker, and this is the sensitivity for certain properties and for certain material properties parameters. And of course, when we have the measurement data, we can match the properties, especially for the suspension. We can check the validity of the 2D model. So what's the validity range? Because there are some assumptions for the 2D model, but we can have an understanding how the tweeter will behave for these properties. Okay, and to summarize that, so there are several options that are available. So we could also use thermoviscose acoustics, and we use some of those because there are thin, narrow regions where we cannot or shouldn't neglect any dissipation. And we can also use an optimization and moving meshes to calculate the distortion of the model. And it's a true multiphysics problem since we have several physics like structure mechanics. We can also calculate the dissipation, the heat dissipation, and vibration is coupled to the acoustic field. So there are at least 3 physics that is included in the model. And the model itself is a fully parametric, the geometry, so you can create different geometries with different membrane shapes, lengths, so they are adjustable. You can change the coils, different materials are available from a drop-down menu, and there are several studies options like the frequency sweep optimization, large deformation, just to name a few, so these are all handled in one piece of model there. And that's the end of my presentation, and thank you. And if you have any questions, feel free, so we have time for that. Yes, Mark?